Hi students, very good morning. Welcome back. Today we are going to discuss about the Bohr model of atom. Bohr model for hydrogen atom. Okay, as we have seen that the J.J. Thomson plum pudding model, in that the positive protons are uniformly distributed, electrons are embedded. And this model is modified by Rutherford. Rutherford proposed a planetary model of atom. In that the positive nucleus, all the mass and positive charges concentrated at the center of the atom called the nucleus. And the electrons are revolving around. Okay, electrons are revolving around. But this atomic model has some drawbacks. In order to overcome the drawbacks of Rutherford atomic model, Niels Bohr in 1913 proposed a new model which is based on the quantum theory proposed by Max Planck. Max Planck proposed a quantum theory. As we know that the radiant energy is in a packet of energy, a definite amount of energy, that is called a quantization. So quantization concept is introduced in the atomic model. Okay, let's discuss the main postulates of Niels Bohr theory one by one. The very first postulate is the electron in a hydrogen atom. The electron in hydrogen atom revolves around the nucleus only certain selected circular paths called orbits. Okay, once again, the electron in hydrogen atom revolves around the nucleus only in a certain selected circular paths called orbits. And these circular paths associated with a definite amount of energy, or the electron in a orbit associated with a definite amount of energy. That's why the orbits are also called energy levels or energy shells. Okay, the energy of an electron in an orbit is definite. That's why Niels Bohr called the energy levels or energy shells. Okay, then the positive nucleus, atom has a positive nucleus. Electrons are revolving around the nucleus through selected circular paths. These are the selected, you imagine that positive center of the atom, electrons are revolving around the nucleus. The orbits are also called energy levels or energy shells. Why? Electron in an orbit associated with a definite amount of energy or definite energies. That's why it is called energy shells or energy levels. And the energy shells are numbered as, the energy levels are numbered as 1, 2, 3, 4, etc. Okay, the orbits are numbered as, first point is orbits. Orbits are energy shells or levels. Okay, these are numbered as 1, 2, 3, 4, etc. The energy shells are numbered as 1, 2, 3, 4, etc. and are designated as K, L, M, N, etc. So designated, numbered as and designated as K, L, M, N, etc. Okay, that's about the first postulate. Once again, electron in a hydrogen atom revolves around the nucleus only certain selected circular paths called orbits. Okay, numbered as 1, 2, 3 and designated as K, L, M, N, etc. The second postulate is, as long as an electron in an orbit, it doesn't lose or gain energy. Okay, as long as an electron in a particular orbit, it doesn't lose or gain energy. This means that the energy of the electron in an orbit is a constant. The energy of the electron in an orbit is constant. What it means? The energy of electron in an orbit is quantized. A definite energy, okay, there is a definite energy for a particular electron. It doesn't lose or gain energy. That means the energy of the electron is quantized. That's why the orbits are also called stationary states. Okay, as long as an electron remains in a particular orbit, it doesn't lose or gain energy. That's why the orbits are also called stationary states. The energy of the electron is quantized. The energy of electron in an orbit is quantized. So, second point is based on quantization of energy. Quantization of energy of electron. Okay, and that's why it is called a stationary states. Stationary states. So orbits are also called as stationary states because if an electron in a particular orbit, if an electron remains in a particular orbit, it doesn't lose or gain energy. Okay, then the third point is, that's why it is called a stationary state. Third point is, if an electron revolving around the nucleus, okay, if an electron revolving around the nucleus, suppose the electron is here and is revolving around the nucleus, there is a distance between the nucleus and the orbit. Suppose it taken as r, okay, or small r is the radius of orbit. An electron has a particular mass, okay, mass of electron we take as me, 9.11 into 10 raised to minus 31 kilogram. And the electron moving with the velocity v, the electron moving with the velocity v, and there is angular momentum. Okay, what is angular momentum? Angular momentum mvr, you studied in physics. Okay, angular momentum is I omega. Okay, I omega. I is equal to m r square. Omega is equal to v by r. Okay, so I omega is equal to mvr. Okay, refer the physics textbook. So only those, the third point. Okay, we are coming to the third point. Only those orbits permitted in which the angular momentum of the electron is integral multiples of h by 2 pi. Okay, so angular momentum, I write here angular momentum mvr is equal to nh by 2 pi. nh by 2 pi. Okay, are you clear? So, if an electron revolving around the nucleus, it revolves in an orbit, r is the radius of the orbit, m is the mass of electron, v is the velocity of the electron, thus angular momentum mvr is equal to nh divided by 2 pi. Okay, how it is defined? Only those orbits are permitted. Okay, only those orbits are permitted in which the angular momentum of the electron is integral multiples of h by 2 pi. Okay, so what is n? N is 1, 2, 3 in the quantum theory. N is equal to 1, 2, 3, etc. What is h? H H is Planck's constant. H is Planck's constant. Okay, I already told you. Niels Bohr explained the atomic model by considering the quantum theory. So MVR is equal to NH by 2 pi. And the next important point, the fourth point. Okay, fourth point. Only electron move from one orbit to the another by absorbing or emitting energy. Energy of the electron is quantized in a particular orbit. If the electron absorb energy, it will move from lower level to the higher levels, lower stationary states or lower energy shell into the higher energy shells. And if the electron at a higher energy shells or higher orbits emit the energy, okay, the electron present or occur at the higher levels emits energy and it returns to the lower levels or jump into the lower levels. Okay, they jump into the lower levels. So by absorbing energy, electron can move from lower level to the higher levels, and by emitting energy, it can jump from higher level to the lower levels. Otherwise, the electron remains in a particular orbit. Are you clear? Yes. Then the fourth point is absorption of energy and emission of energy. Movement of electron. Movement of electron in different energy shells. In different energy shells. Electron absorb energy, it move from lower level to the higher level. Electron emits energy, it will move from higher level to the lower levels. That's about the fourth point. And the another important point is the frequency of absorbed or emitted radiation or electron emitted light. Okay, when the electron jump from higher level to the lower level, energy is emitted. That energy comes in the electromagnetic spectrum. So the frequency, okay, the frequency of the absorbed or emitted by the electron differ by delta E. Okay, the frequency of the electron wave or electron differ by delta E. Let's consider one important thing. Okay, I just erase these things. Suppose the electron is at a lower energy level E1. Okay, first energy level. Suppose the electron is at the first energy level, lower level. Okay, generally lower level. What about the energy of that electron? It is directly proportional to the frequency. H nu 1. We have to take H nu 1. And the electron by absorbing energy jump into the second level or higher levels. Okay, electron is jump into the higher levels. What is the energy of that electron in that level? It is H nu 2. What is the difference between the energy? Energy difference. Energy difference is equal to E2 minus E1. Okay, E2 minus E1. Then what is E2? H nu 2. Okay, or I write here E2 minus E1, H nu 2 minus H nu 1. E2 minus V1 is written as delta E, change in energy, delta E. Then H is common, H is nu 2 minus nu 1. Okay, H is equal to 6.62 into 10 raised to minus 34, which is Planck's constant. Okay, which is known as Planck's constant. Then delta E is equal to, I can write that H nu. Why? The difference between two frequencies gives another frequency. Okay, so the difference of frequency is frequency itself. Or you can write a nu 3, no problem. So delta E, change in energy is equal to H nu. Nu 2 minus nu 1 is equal to nu. Then what is the frequency of radiation emitted by electron or absorbed by the electron? It is delta E divided by H. Okay, delta E by H. Again we concluded that the electron in an atom, okay, in a particular energy level, and the energy level is quantized. Okay, it has a definite amount of energy. Okay, very simple. The energy energy of the different levels are quantized, and the difference between the two energy levels is also quantized. Okay, again we concluded that the energy of the electron in an atom is quantized. Energy of electron in atom is quantized. So by using quantum theory, Max Planck quantum theory, Niels Bohr successfully explained the structure of the hydrogen atom, or he proposed a new model for hydrogen atom. Okay, next we discuss about the merits of Niels Bohr atomic model. The important merits of Bohr model are: the first one, he could explain the stability of an atom. Okay, the first merit of the Niels Bohr model is he could explain the stability of atom. As long as an electron remains in a particular orbit, the electron doesn't lose or gain of energy. That is, the electron remains in a particular shell. As in the case of Rutherford, he couldn't explain the stability of atom because if the electron revolving around the nucleus, it continuously irradiates its energy and finally it collapses into the nucleus. Okay, that's we cannot accept. So in Bohr model, the electrons are revolving around the nucleus through a certain circular paths, and the electron in that particular orbit doesn't lose or gain energy. That's why the electron is in that particular shell, and that's why he could explain the stability. He easily explained the stability of atom, okay, as using quantization level. And the second important merit is he could explain the hydrogen spectrum. Rutherford couldn't explain the hydrogen spectrum because in hydrogen spectrum there are several lines. Okay, many lines in the hydrogen spectrum. Rutherford couldn't explain the hydrogen spectrum. But Niels Bohr or Bohr model could explain the spectrum of hydrogen or hydrogen spectrum. In the case of hydrogen, only one electron present in the atom. In hydrogen atom, only one electron present. If we supply energy, the one electron present in the ground state, that is the lowest stage, okay, the ground state, excited into higher energy levels. You know what is excitation? If an atom or electron or a molecule absorb energy and goes into the higher level, it is called excitation. So if an electron absorb energy and excited into higher energy levels, okay, look at here, okay, if the hydrogen atom, we consider the hydrogen atom, one electron present in the first orbit. You remember that first shell, second shell, third shell. Okay, the shell is written like a line for convenience. Okay, for convenience, we take it as a straight line. If the electron is in the first level, it is called a ground state. Okay, the first level of hydrogen is also called the ground state. And if the electron absorb energy, what happens? It jumps from lower level to the higher energy levels. Okay, second level, third level, fourth level, fifth level, sixth level, seventh, eighth, up to infinity. Okay, the higher levels are second, third, fourth, fifth, sixth, etc. to infinity in the case of hydrogen atom. Since the sample of hydrogen contains many hydrogen atoms. Okay, can you follow me? Okay, the sample of hydrogen, we cannot take a single atom. The sample of hydrogen contains many hydrogen atoms. So different hydrogen atoms absorb a different amount of energy. Different hydrogen atoms absorb different amount of energy, and the electron present in the hydrogen atom occupy different energy levels. Okay, the electron present in the hydrogen atom occupy in the different energy levels, maybe in the second level, third level, fourth level, fifth level, or is at a free, that is infinity. Okay, it is a lack of attraction between electron and nucleus. We can say that infinity. Okay, so the different atoms are absorb different energy, and therefore the electrons are present in the different energy levels, and the excited electron can come back into the lower levels. Okay, by absorbing energy, the electron jump from lower level to the higher levels, and the excited electron, that is the electron present in the higher levels, can come back into the lower state by emitting energy. And if the electron emits its energy, it back into the lower state. And during this emission of radiation, the frequency or wavelengths are associated. Frequency or wavelengths are associated with this emission. Okay, let's look at this picture. If the electron present in the second level back into the first level or ground state, one line is obtained. And if the electron present in the second level back into the first level, another line is obtained. And third level to first level, fourth level to first level, fifth level to first level, and infinity to first level. This is a series of line that comes under the Lyman series. We cannot see this, okay, because it is in the UV range. Lyman series is obtained by the electron from higher level to the lower levels. Which lower level? N is equal to 1. Remember that? In the last class, I give you the information for Lyman series. Lower level is N1 is equal to 1, and a higher level N1, N2 is 3, 2, 3, 4, 5, etc. So from the higher levels, 2, 3, 4, 5, etc. to infinity, back into the first level, we obtained we get a series of line called Lyman series, which is in the UV region. And in the second possibility, the electron present in the third level back into the second level, fourth level back into the second level, fifth level to the second level, fourth into the sixth, seventh, eighth, etc. And the last line is infinity to second. And this series of line, the returning of electrons from the higher level to the second level. Okay, here the lower level is n is equal to 2. We get a series of line which is called Balmer series. Okay, Balmer series. In that we can observe these lines from red to violet. Okay, I have only some colored chalk. That's why I draw the red, orange, yellow, blue, green, violet. Okay, the Balmer series lies in the visible region of the electromagnetic spectrum. Okay, can you follow me? The Balmer series obtained is lies in the visible spectrum. Okay, visible region of the electromagnetic spectrum. And another possibility, another thing, if the electron present in the fourth element back into the third, fifth to third, sixth to third, seventh to third, eighth to third, last infinity to third level. So here the lowest level n is equal to 3 and the higher levels are 4, 5, 6, 7, etc. And that is called a Paschen series. Okay, P-A-S-C-H-E-N, Paschen series, which comes in the IR region. The next is to distinguish the series I gave color. Okay, the next possibility is 5 to 4, 6 to 4, 7 to 4, 8 to 4, infinity to 4. That series is called a bracket series. Okay, bracket series, which also comes in the IR region. Then next is 5 to 4, 6 to 5, 7 to 5, 8 to 5, and infinity to 5. That is called a fund series, or sometimes you know that P funds. Okay, it is correct pronounced as fund series. And one more series I gave you, Humphrey series. In Humphrey series, the electron back into the 7 to 6, 8 to 6, and infinity to 6. Are you clear? So Niels Bohr successfully explained the spectrum of hydrogen. Bohr model successfully explained the spectrum of hydrogen by using quantized energy levels or by using orbits. And one more important information. This is the first line in the Lyman series. N1 to, so I write here. N2 to N1 is the first line. N3 to N1 is the second line. N4 to N1 is equal to the third line. And N infinity or infinity level to 1 is the last line. Okay, it is very important in the competitive examination. Also in application level question. The first line in the Lyman series, n is equal to 2 to n is equal to 1. Second line in the Lyman series, n is equal to 3 to n is equal to 1. Third line in the Lyman series, n is equal to 4 to n is equal to 1. And the last line in the Lyman series, n is equal to infinity to n is equal to 1. Similarly, you can understand that Balmer series, first line 3 to 2, second line 4 to 2, third line 5 to 2, and the last line is infinity to 2. Okay, you understand the Paschen series, bracket series, and the fund series. Okay, first you understand the Lyman series, first line, last line. Similarly, Balmer series 3 to 2 and the last infinity to 2. Then you can easily understand the first and last line in the Paschen series, bracket series, fund series, etc. A very important information. Okay? Yes. Then, so the first merit is he could explain the stability of atom. Second merit is very important. He could explain the hydrogen spectrum. He could explain the hydrogen spectrum. And we move to the third important merit of Niels Bohr. Okay, the third important merit. First is stability. First stability couldn't explain. Stability is explained by Bohr. Second one is hydrogen spectrum. And the third one is energy of electron. Energy of electron in the nth level. Energy of electron can be calculated. He calculated the energy of the electron in the nth level. Okay, first we write En by using the equation minus 2 pi square m e raised to 4 n square h square minus 2 pi square m e raised to 4. Okay, m e raised to 4 divided by n square h square. Why you know that? Okay, 3.14. M mass of electron. E charge of the electron. N first level, second level, N is varies. Then H, Planck's constant, and En is equal to minus 2.18 into 10 raised to minus 18 joule divided by N square. By knowing these values, okay, these values we know that pi value, mass value, electron charge, then Planck's constant, all these values we know. By substituting the value, we get minus 2.18 to 10 raised to minus 18 joule, and also is equal to, can be expressed in electron volt, minus 13.6 electron volt divided by N square, minus 13.6 electron volt divided by N square. It is per atom. And another important thing is energy is expressed in the kilojoule, minus 1312. Okay, kilojoule per mole. Here it is expressed in per mole N square. These are the important equations to calculate the energy of the electron in a particular orbit. If n is equal to 1, you substitute n is equal to 1, n square, 1 square, and n is equal to 2. E2 is this value divided by 2 square. If you want to calculate the energy of the third level, n3, so 3 square. Okay, you practice at home. You practice the different values at home. So this is the third important merit of Niels Bohr atomic model. Okay, are you clear? And in some cases, it is written like this: En is equal to RH. Okay, minus RH divided 1 divided by L square. Sometimes written like that. Where RH is the repair constant for hydrogen, minus 2.18 into 10 raised to minus 18 joule. Okay, so if you put a minus here, you don't put a minus here. RH is equal to 2.18 into 10 raised to minus 18 joule. Okay, that is the energy calculation. Another important merit of Niels Bohr is he could calculate the radius of the orbits. He could calculate the radius of the orbit. This is the third important application or merit. The fourth one is he could calculate the radius of the orbits. Okay, by using an equation, we can calculate the radius of an orbit. Rn is equal to n square a0, where a0 is equal to 52.9 picometer, or is equal to 0.529 angstrom. Okay, in your textbook, I think 52.9 pm is given. Also, you know that to calculate the radius in the angstrom, 0.529 angstrom. Okay, so that is the value. Or you have to write R1 is equal to, what is R1? R1 square. First shell. 1 square into, what is A0? 52.9 picometer pm. And what is the value? That is 52.9 pm itself. Okay, you just calculate R2, R3, etc. Okay, you can calculate the R2, R3, etc. So, what are the important merits of Niels Bohr? He could explain the stability of atom. He could explain the hydrogen spectrum by the excitation of electron and back into the lower level. And the third important merit is he could calculate the energy of the electron in an orbit. Okay, energy of the electron in an orbit. Okay, three different equations I gave. Minus 2.18 into 10 raised to minus 18 joule per atom. If you want to calculate the first energy level, you put 1. Okay, 1 square. Then if you want to calculate the second level, 2 square. Like that you do it. Okay. Then we discuss about the energy difference between the two levels. Okay, energy difference between the two levels. Delta E is equal to. Okay, first I write the E1. Okay, En1 is equal to minus 2.18 into 10 raised to minus 18 joule per atom divided by N1 square. And that about N2. N2 is equal to minus 2.18 into 10 raised to minus 18 joule per atom. Okay. Then delta E. What is delta E? Delta E change in energy. Delta E is equal to E2 minus E1 or En2 minus En1. Are you clear? Yes. By subtracting this value from this and rearranging, we get 2.18 into 10 raised to minus 18. Okay, minus of minus. Okay, E2, this value minus this value, minus of minus plus, then 2.18 to the 10 raised to minus 18 is common into 1 divided by N1 square minus 1 divided by N2 square. This is the energy of electron transmission between the two levels. The energy change between the two levels can be calculated by using this equation. Okay, also in electron volt, also in kilojoule. Only the constant changes. Okay, so energy difference between the two levels can be calculated by using this equation. Are you clear? Okay, similarly, you find the frequency difference. Okay, as earlier we know that frequency difference, I write here, frequency is equal to delta E divided by H. Okay, delta E divided by H. By knowing the frequency, we can calculate the wavelength of the radiation. Wavelength of the radiation. So that's about the merit of Bohr model. So today we have seen that Bohr model of hydrogen atom. In that 5 main postulates. Okay, I think you understood the concept. Please write into your notebook. And also the merit, 4 important merits of Bohr model. One is stability, explain the stability. Second is hydrogen atom. Third one is energy calculation. Fourth one is radiance calculation. From energy calculation, we can also find the change in energy between the two levels. Delta E is equal to E2 minus E1. That is equal to 2.18 in 10 raised to minus 18 joule. 1 divided by N1 square minus 1 divided by N2 square. Remember that this N1 is less than, always less than N2. Okay, remember, you also at that point, N1 is always less than N2. And next section we will discuss about the problems based on Niels Bohr concepts. Okay, also the drawbacks. Drawbacks and problems based on the Bohr concept we will discuss in the next class. Thank you.